nuestro sexto Simposio Internacional de Túneles y Lumbreras en Suelos y Rocas, mismo que es organizado por dos.
Come to this international congress that is organized by two Mexican associations, Mexican Association of Tunnel Construction and Underground Works and the Mexican Association of Geotechnical Engineering. I am Dr. Luis Carlos, Vice President of one of these associations, and I will be the moderator during this Congress. First of all, we are going to start with the inauguration ceremony. We have Mr. Mario Salazar Lascano, Chairman of the Mexican Association of Tunnels and Underground Works. Dr. Roberto Avelar Cajiga, President of the Mexican Association of Geotechnical Association. I will give the floor to Mr. Mario Salazar Lascano. You have the floor, Mario. Thank you, Ricardo, and everyone, ladies and gentlemen, from Mexico. On behalf of the Mexican Association of Tunnel Construction and Underground Works, I welcome you to the 6th International Congress of Tunnels and Shafts in Soils and Rocks that the Mexican Association of Geotechnical Engineering have organized. Welcome. This is just the beginning to take advantage of the advantages that the great experience of different colleagues from different countries give us in our task. Thanks to the technology, this will give us the opportunity to listen from anywhere in the world to experts in these topics who will share with us their experience and knowledge about international projects, study cases, and about the use of underground spaces. Young engineers will also give us their scope and experience, which will allow us to strengthen our activity and also to find tools in order to face the challenges and uncertainties that we have in the development of our professions. Our work demands us to be updated and to, of the quality and accurate execution of our work, and this depends on the expertise of many people. Undoubtedly, all of us are interested in knowing more and to contribute in projects that will benefit the society with technology. On behalf of Amitos, I thank the speakers who are very generous to share with us their time and their expertise with all of us. I also thank the Mexican Association of Geotechnical Engineering and its chairman, Dr. Roberto Aguilar Cajiga, as well as other organizations for their work in the 6th International Symposium on Tunnels and Shafts in Soils and Rocks. I welcome you very warmly with the certainty that this symposium will achieve the goals that we have. And well, have a good day and a very fruitful symposium. Thank you. Good morning, everyone. Good afternoon on the other side of the Atlantic. Welcome, everyone. I am Roberto Velar Cajiga, and it is an honor to chair the Mexican Association of Geotechnical Engineering. It has had the opportunity to work with the Mexican Association of Tunnels and Underground Works in Soils and Rocks. all the participants have joined this effort, and I thank them very much for their work before this symposium. As you may have seen in our agenda, during 4 days of the symposium, we have very interesting topics. In each of the sessions, we will have keynote speakers that are very well well known for their experience and expertise. And we will talk about very different topics on underground works, and they will facilitate the development of this symposium. We also have international and national speakers. There is a session that I am very enthusiastic about because it is coordinated for and by young engineers, and they will share with us their experience and their knowledge, and it will be very important for all of us. Mr. Mario Salazar, I thank him very much for his support. And he was telling me that the synergy of all these Association of Geotechnical Engineering has spread out through this international symposium of tunnels and shafts in soils and rocks, and they are also spreading out all this knowledge and expertise, and we are joining both associations for the sake of our task. Before giving the floor, I want to tell you that the Mexican Association of Geotechnical Engineering was started in 1957, for which this year we are celebrating the 65th anniversary of this association. Thank you very much to all of you. Welcome to our event. I am certain that you will find it very interesting. Thank you. We thank Mr. Mario Salazar and Mr. Roberto Avelar, President of Amigos, and the Geotechnical Engineer Association. We will start with the first technical table that is about technical innovations applied to tunnels and underground works, and I will give the floor to Mr. Roberto Gonzalez. Welcome. Hello, good morning. It is a pleasure for me to be here with you. I would like to thank Amitos for giving me the opportunity to chair this first session of latest technologies applied to tunnels and underground works. We have our first speaker for the keynote lecture, which is Mr. Lok HOME, who will talk about mechanized tunnels, but with a non-circular section, which we think is a very important innovation in tunnels for mining, where a flat floor is needed so that trucks can go through the mine. I will read a little bit about Mr. Lok HOME. He is very well known. He does not need a lot of introduction. Lok HOME,
after graduating with a degree of mining technology from Haley Borey School of Mines in Ontario, Canada. Between 1965 and 1968, Lok worked as a project manager at several Canadian mines before joining Robbins in field service, where he then progressed through several management positions. Lok served as president of Atlas Copco Jarba from 1980 to 1985, then founded Bortec Incorporated. Bortec later acquired Robbins in 1998 and unified the two companies under the Robbins name with Lok as president. Today, Robbins is a worldwide business that supplies all types of tunnel boring machines, related equipment and services. In addition to his role at Robbins, Lok is also active in the tunneling industry associations, He's a key member of the International Tunneling Association, the ITA, as is on the steering committee of the advancement of the industry standards and ideas, known as ITATEC. He has been active in the US Tunneling Society, UCA of SME, and has served as director on several occasions. Without further ado, please, Mr. Home, go ahead with your presentation.
You're free to speak. Yes, hello, everyone. It's a pleasure to speak at Amidos. I've been to several of your conventions, and I really respect what the strength of your organization and also the friendship in the organization. So again, it's a pleasure to speak to you, and I'm speaking to you from Texas, so I'm not so far away, and I was even able to visit a job site yesterday, so it's kind of an interesting combination of events. So I'll start into this presentation. This presentation is mainly about how technology and innovations come about in our industry. And it's different in mining than it is in civil. We'll talk this morning about a square machine or rectangular machine. It's actually a rectangular machine, as you can see on the screen. And you're looking at the tunnel itself that's completed with this, what we call mine development machine 5000. And the tunnel is, as you can see, there's no concrete in it. It's just a excavated tunnel, a rectangular tunnel in rock. It is, although not so apparent, but it is all screened up in the roof, and we'll get into that a little later. And this is non-circular. I'll concentrate a little on what has gone on in non-circular tunnels over the years in our industry, and then come back to this machine itself, how we did it. And what's interesting about it is the contractual arrangements that let's say that lead into or facilitate innovations, to allow you to design a machine like this and get it underground and understand who takes the risk. Because as we all know, if you're going to innovate and come up with completely new technologies, it never goes all right 100%. You're never that fortunate. And you need a mind to, or a good customer to work on innovations. In civil construction, innovation is different. And the main reason innovation is different in civil, there's been a lot of innovation over the years, but on a civil project, the contractual arrangement is usually a municipality that needs a tunnel done. It's a one project tunnel mostly. It's not there for years. And the owner doesn't want to take much risk. He's responsible to really the citizens, it's a city, and so he doesn't want to get involved with much risk. And since it's only one project, he isn't so keen on trying to innovate. That unfortunately is the fact. So innovations come about in civil mainly because we get into trouble and we have to come up with something new. And that was sort of demonstrated in Emisor Oriente in Mexico City when we had those machines and not enough geological data. And there quite a bit of innovation went on. And the client was very obliging to help us with that innovation, us meaning the contractors, the TBM suppliers. And there was a couple of us TBM suppliers down there, and innovation went on both of those projects. In mining, it's quite different. In mining, the mine has a really long-term outlook in what they're trying to do. They're going to buy MDM 5000, and they're going to operate it for the next 10 years. And what they're looking for is sort of a 5 or 10 year window, not just that one project. They want to get to their ore body faster and drive, be able to access their ore body faster. So they're very much interested in improving the technology. And so it's different in the between civil and mining. I'll give you a couple of examples of what we've done in mining. This is an access tunnel to a coal mine where we bored a decline. It's a mine in Australia, 8 meters diameter. And here we used, in this case, we were using some of the technology that we learned in Emisor Oriental and used it for this mine application that started out from surface, went down a grade 1 in 6, well, there was 2, 1 in 8 and 1 in 6, and it bored down starting out in soils and some water formations, then into mixed phase, and then into final rock, and then through some coal seams down to the main coal seam where they were going to set up longwall miners. And no one had ever done this before, or there was in terms of, starting from soil, going into rock and down to the coal seam at an angle. And in this case, the mine was Anglo-American, actually bought the machine from us. We sort of negotiated the specs with Anglo and some consultants, but they purchased it. They came right out and purchased the machine. And then they hired a contractor to operate it, an experienced contractor that had some TBM experience, not much. And so the financial arrangement was somewhat complicated, but the mines are used to that. And so, yeah, this machine bored this decline, and it was also kind of unique because it was something the miners had never seen before. I mean, most of it in civil contractor were pretty used to these segments, and the mine was delighted to have a nice lined tunnel for once. And but it's expensive, but they're going to be here for 50 years, so they don't mind putting in an expensive tunnel. And what happened is the machine bored down. We left the outer skins in the tunnel and walked the machine, actually made a walking device to walk the machine back out of the tunnel, and then moved it over and bored the second tunnel. And that all, I mean, we had some problems in the beginning, like everything else when you try to innovate, but we sorted them out within weeks, I would say. And had to be explosion proof. And then they just put this concrete floor in afterwards, and that's their access tunnel. They drive vehicles in and out of this access tunnel. So it was an interesting process and an example of good cooperation. The project sort of finished ahead of schedule, actually, which is, I have to admit, a little unusual for when you're putting in innovation, but it finished somewhat ahead of schedule. They said it was 14 times faster if they'd gone and done this with a road header. And to a mine, that means a lot. That means that you get to the ore body, you get your coal sooner, and there's tremendous, I don't know what the number is, but there's probably $1 billion in development work before they get their first ton of coal. So the sooner they start to produce the coal, the sooner they can get payback on their investment. So it's very important to have a fast access to any ore body. And the mines understand that, and they're willing to take some risk to do that. This mine development machine we got, this non-circular machine, the MDM, is at the Fresnillo mine, and they're looking, it's underground. I think it's 650 meters underground. Had to take it down the ramp and assemble it underground. And what they're looking for is a parallel access to the long continuous vein they have. And they want to mine out along the vein faster than they can with drill and blast. So that was the requirement, and that's where we started from. Non-circular isn't sort of unique. It's been done in the civil industry quite a bit. And you can see here's one example. Most of these civil non-circular tunnels are done in Japan, and they're all done in soil and clay. These cutting wheels that you see at the top picture there, they don't really cut a square tunnel. They sort of cut nearly a square tunnel, and the square is sort of trued up by the shield itself. you actually push the shield forward with jacks, just like you do with a single shield. But because it's clay or soil, you can finish up and finish the cut by just pushing the shield into the clay and ending up with effectively a rectangular square tunnel. There's complications and a little complicated as you saw in the lower one, how you put your segments in, but that's been done and been done successfully. In our case, we don't have the luxury of pushing the shield through the rock. You have to actually cut out the square. And the reason they want flat bottom, the mine, is there's probably in Fresnillo 20 different vehicles used in their mining operations. There's everything from service trucks for their industries to haul trucks to front end loaders, drill jumbos, everything going on in this mine. And so they're very important to have a flat, good floor. And yeah, they respect mechanical excavation, but they respect that flat floor a lot more and look for that. So in drill and blast, it's just sequential. I would say it's more dangerous. It's just not as fast as we can mechanically excavate. So in this case, we went to the mine and decided on what shape and profile we could do and ended up with this MDM. Here you can see just the rock support going up. We're, of course, great believers in never getting under unsupported ground. So we're always rock supporting before as we go. And here, of course, we could bore a round tunnel and put an invert in, but as this diagram shows, you end up with nearly 50% more muck to get the same operating window. And that in a civil project, maybe that's not so bad. But in a mine where you're 650 meters underground and you got to get rid of every ton of ore, haul it out to the shaft, hoist it up the shaft, 50% more volume is a big deal. There's been quite a few attempts over time to look at how to excavate hard rock in non-circular. And as you can see here, there's been a number of attempts, and some of them worked out, nearly worked out, others didn't work out at all. And the most successful ones are the ones that are done with road headers, but road headers, like the top photo, road headers have their limit in terms of hard rocks. Certainly, even in some rock as in 50 MPa, they start to run up against advanced problems, too much pick consumption, other problems. But at 100 PSA rock, 100 MPa rock, they're essentially stopped. It is very rare, even with the most high-tech modern road header, it can't effectively operate in 150 MPa rock. It just doesn't happen. So that's the biggest use of underground mechanical excavation are road headers. There's been attempts by different companies in the last 20 years to go non-circular using oscillating cutters, vibrating cutters, undercut principles, mini discs. And I won't go into all the different ones here, but you can see this one below the yellow one, that's sort of a combination of a oscillating cutter and a undercut principle, which has been around for 40 years, which hasn't proven up so well. The one to the right of that is sort of a very high power road header. And that there's one of those being tested right now in one of the mines in Ontario, Canada. And with respect to all the manufacturers, it's got a couple of disadvantages. And one of the disadvantages is that you want to, you got to put in ground support fairly early. And when you have a boom, you can't do that very well. Why does standard TBMs, why do they work, or why do they work so well, or what is the principle? Well, the principle in our case is we use disc cutters on a round machine. And as you can see on the left, the guy standing in between the cutter head and the cut rock is not in a good place, and probably from a safety standpoint shouldn't be there. But anyway, the photo demonstrates fairly well the grooves that you cut. And the photo on the right here shows how, you know, this cutter works. The rock, the cutter makes these big cracks in the rock and just rotates around, keeping these cracks going. And we keep this spacing usually about 75 to 100 millimeters. And the trick is to stay in the same groove all the time. And we use that principle in the MDM. It actually stays, the disc cutters are always in the same groove, cutting and recutting the same groove as it is in a round TBM. There's been attempts to use disc cutters on rotator type machines. This is an example of one. They've got sort of mini discs on a rotator. But the problem with that is it also has I mean, you come up against the limits of what you can excavate, because the discs are so small, you can only get a small bearing in them, and therefore you can't put the big loads you need into the face to cut hard rock. And then you have the very added distinction that if you look at the comparison between the 5-inch disc or the 125 millimeter disc and the 17-inch cutter, you can see the big the wear difference. What you do in a disc cutter is you wear down the steel until it gets to the bottom of the shape of the disc, and then you have to change it. So if you have a really small diameter cutter, of course, that wears out very fast. I mean, there's probably 25 times as much wear volume in that 17-inch cutter as in that 5-inch cutter. So you can see why the principle of using mini disc didn't work out so well. And Robinson's been at this damn trying to make these squared tunnels or non-regular times. And this machine was an attempt down in Sydney years ago, I would say in the late 70s, early 80s. And there we had you can see we were using disc cutters, but the disc cutters were in a swinging motion like we're doing in the MDM, but also they moved out laterally. So you not only swung vertically and then you made a cut, then you moved out the arms. And between moving out the arms and swinging vertically, it was kind of a slow cut. And in this case, these tunnels were used for sewers mainly. So it was just concluded that round was just as, you didn't get a great advantage off the non-circular tunnel, and round was really efficient. And so the industry, Atlas Copco made some of these similar machines, and the industry just kind of gave up on it and went round when you were there for sewers. Of course, Robin's big attempt about 15 or 20 years ago was the mobile miner, where we had a big rotating drum out front with cutters mounted all around. And we built 3 of these machines, and one we used in a civil project in Japan, and 2 of them we put into mines. And we had medium success with it, but it wasn't a very effective, there was 2 or 3 things wrong with the cutting principle. There's the cutter head, of course, the drum rotated and the cutter head swung from left to right or right to left, but it didn't stay in the same groove, which made it inefficient cutting. And then the other problem with these types of machine is the cutting force right out here on the left-hand side where the cutters enter the rock is a long way from the force reaction system, the grippers, which you can see 2/3 of the way back. And because of that, you have a sort of an unstable cutting system, and you need some very heavy beams and structures to react that load. It had some success. It bored several hundreds of meters and was successful. It was slow, but you can see it made a beautiful tunnel, and it had the advantage of having variable widths too. But eventually the mine, which is a problem for the mines, in this mine, it was a copper lead mine, and the copper prices or lead prices went down. And so and this was not a critical tunnel, so they kind of gave up on it. This thing had potential, but they just gave up, and not much work was done by our company or other companies for 20 years after this to go non-mobile. Now there's a revival of mechanical mining companies. I mean, mining companies wanting these mobile miners. This is just a cross section of the machine with a cutting wheel, and it was somewhat mobile. I mean, we called it the mobile miner, but it is about as mobile as a D8 Caterpillar. Not exactly mobile, but we did have crawlers under it, and you could back it up and you could go forward. But you couldn't turn a 50-meter radius what the mines want, or a 10-meter radius, which would they prefer. So it was semi-mobile. A little on the mine development machine that we've got operating in Fresnillo, and we've got operating in Fresnillo. So this is called the MDM. It's we assembled it in our workshops in Ohio. It was designed to cut a rock up to 200 MPa, and it was to cut a 4.5 to 5 meter drift. And what how it works is it's a full dress of cutters. These are double disc cutters, but the double discs are there so that we can get the spacing we want and acceptable bearing capacity within that cutter. They're 18-inch cutters, and they stay in the same groove. And what we're doing is swinging that cutter head up and swinging it down. We don't do, in most cases, we don't do full swings. We're trying to stay buried in the rock as much as possible. So we'll do a series of center swings, then we'll do some gauge swings, and then center swings and gauge swings, full swings, or 180 or more. Because you have to sweep and get the last cutters out of the pattern, you end up with not a 180-degree swing, you end up with more like a 220-degree swing, because you got to get your gauge cutters out of the cut to keep the profile you're looking for. What's interesting about the MDM, you see the big R up front, that's the front gripper. So we're reacting the force fairly quickly, but find the cutting action, the actual cutters themselves, they're only 2 to 3 meters from the cutter entering the rock to where you're taking the forces out. And that's kind of one of the keys to design. If you get farther back and react that, you end up with just more steel in the tunnel, and just you have to have a bigger, more structurally strong machine. The closer you can take it out, effectively, the lighter the machine is. We got a two-stroking system. We got behind the cutter head, there's 2 big cylinders that force that cutter head. And we're trying to, with those 2 cylinders, we're trying to, let's say, reduce the effect of comma cutting. Comma cutting is, of course, when you got a rotating cutter head or a swinging cutter head, you enter the rock and the cutter's barely cutting the rock. You get to the center, and then it's fully buried, and then it exits. And we're at TBM, round TBM, you're buried all the time. So you're trying to replicate with this cylinders behind the head, we're trying to take out the comma effect. We're also experimenting. You can see we've got rear grippers on this machine back farther, and we're experimenting with whether we're better off to, let's say, slide the front gripper as we do in a main beam machine and push with the rear grippers, because we got a much longer stroke. So we're working on trying to optimize the advance rates with this machine. This photo, of course, is you can see the ground support. You can see where the gripper's gripped in. We're looking at the front of the machine. Actually, as this photo was taken, they kind of backed the machine up. And so the cutter head is down. The roof shield is down. You can see the guys doing some work behind the roof shield. So it's kind of an interesting shot, just how the machine works and how the cutter head rises and lowers, and we can back up and move forward. But we are gripping. We don't have a crawler under this machine when we're operating. Oops, sorry. You can see here some of the installing some of the ground support. It's all wire meshed. Here, in the picture at the bottom, you can see where they hit some bad ground and put in some actually some McNally systems. That's what these rebar is. So we want to protect that. We're very conscious in anything we do in our machines. We're very respectful of ground support. It's just one of our key things that's in our minds all the time when we design these machines. That's a cross-sectional view of it. You can see some gauge cutting at the bottom. Gauge cutting it complicates the even in round or any kind of machine, cutting the gauge is kind of tricky. You can see on the C1 where that's the conveyor, we're hauling out by conveyor. We did take the machine down a ramp from surface underground, and we used crawlers to do that. This is the cutter head coming down and ending up at the machine. So we took it down, I think, in about 15 different loads and assembled it underground. This is the underground assembly chamber where we're putting the machine together. It didn't require such a big, let's say, underground chamber to assemble it, but we certainly needed the chamber to assemble the machine and get it operating. What has gone right and what's gone wrong? We've had, we actually cut one of the problems we did, or one of the errors, I would say, or where we can improve. We really were too aggressive on that gauge. We took a real sharp, we took square or rectangular, I think, past the limit we should have, and we didn't have enough gauge coverage in our cutters. Looking back at it, we're going to actually extend that gauge out. You don't need that sharp up gauge for even a rectangular tunnel because the wheels on just about any vehicle are in, whatever it is, 250 millimeters or quite a ways in from the tunnel. So you don't need that tight of gauge. And that was one of the, let's say, oversights we did. And we had problems with the scraper. We didn't get that right. It wasn't heavy enough. We're trying to swing and move the scraper as we did. So we had to remove or, let's say, revise the scraper as we scrape into like a rotator, scrape into gathering arms or gathering wheels, and then put it on a chain conveyor. And there was problems with the chain conveyor we had to improve. We also had problems as actually hit some real soft ground, and the machine was effectively sinking. And so we repaired the apron as well as extended the front shoe. So we weren't without our problems, but the mine's real good to work with, and they understand that it's a innovation and that improvements are required. And so they give us the respect and service and help us through this. What happened is on the project, we were supposed to bore about 5,000 meters straight. This red line through here is the main silver vein in that mining district. But there's other veins, as you can, as we got out farther, they were carrying on exploration and they found all these additional veins. So they said, hey, can you bore a big semi-circle tunnel and come back, and we want to pick up and start mining these veins, give us access to them. And we did that, but we were in unknown ground to them and unknown ground to us, and we hit a couple of sections of bad ground, and that slowed us down quite a bit. And you can see where we are, and we're about where that arrow is, and we've been stopped for a while just addressing this fault zone. And the fault zone is giving us a little more problems than we expected. But hey, to get us through a fault zone and with drill and blast is also problematic. So it's a question of getting your mining method right and going through it. This is just a section where we started into this bad ground. You can see it started with a lot of water coming in. Yeah, can you just start the video? Yeah. Yeah, this is water coming in. This is a slowed down cutting action. You can see face fall because that cutter wasn't rolling when we first started it, and you can see where it starts to roll, but it was face fall out. Yeah, so not uh, not a good scene when you got a whole lot of water that is 50 degrees C and and the ground starts to ravel on you and come in on you. It's you know you're starting heading into troubled ground. Uh, so we want, and I think an error is that we weren't disciplined enough, the contractors, the operators, and us to do enough probe drilling ahead, ground detection ahead, and we should have picked up more on this fault. We actually know better, and we're going along, and like everybody else, everybody when you get some success, all you want to do is get more meters the next day, and so you let down your guard, and I think that's what caught us here a little. We still need to make some improvements on this machine. We have to really revise some of the how we steer it and everything. And that was interesting. Although we built a lot of machines and have done a lot of even non-circular work, even the steering, how you steered this machine and what was the correct steering without overloading your cutters and how to steer and get good ground support. All these things were new to us. They're quite different than they are in a round tunnel. And you don't have the experience level from that you depend on when you go round. We're always making improvements on a round machine. And you can't carry all those improvements into a totally new machine. So you have to start a learning process over again. But anyway, they've got a nice tunnel. They love this tunnel because they know where the wall is every meter. It's not rock broken, irregular rock surfaces. You can see there the tunnel conveyor running in the center of the picture up top. You can see the vent line, and other service lines going in. And all this is happening as the machine is progressing. We bored about 1,700 meters, and the best day we got best week we got was 52 meters, and the best month is 191 meters, which is for us in the tunneling world kind of not very fast production, but for the mining world it's double what they get. So yeah, so you got to adjust your expectations, I guess. What's going to happen in the future? What'll occur? The mines want more tighter turning radius. I think we can do that, but we will never get to what you can do with a drill jumbo and make those radius. We just won't get there if we're going to mechanically excavate rock, at least not in the foreseeable future. I think we'll see more use of conveyors in mines. That'll happen. I think the mine planning has to adjust. They got to look at their mine a little differently. They need to get to their ore bodies fast, so we can help them with that. But the mines, I think, will look a little different as they start to move into more mechanical excavation of rock. I think our cost per ton of actually mining with a round TBM are in the same range as cost per ton for drill and blast. So, the mining industry is starting to see that, to understand that, hey, it's possible in some ore bodies to really excavate the ore body with a mining machine. Right now, it's very specialized ore bodies, but I think we'll see a trend in that direction. Of course, tunnel boring and mechanical excavation is far safer and environmentally more friendly. I'd rather be on the in a operator's cabin at TBM than down at the drill jumbo in a mine. So it's more operator and safer and friendlier. And we, what's going to happen in the tunnel? Well, one, we've of course done around for years, and have to say, we understand, we can predict the advance rates, we can predict the cutter costs, and MDM, we're coming along, we'll make further improvements. But the MDM has another disadvantage other than not being so fast. It has a flat roof. That's all right at Fresnillo mine, but there's lots of places where you prefer the round roof, as we show below. And we've got designs to come up with this sort of tunnel with a question mark on it. We understand, using some of the experience we have in the MDM mobile miner and other machines, we are ready to tackle the question mark at the bottom. So I think there you'll see more development in non-circular tunnels, and I think we'll see, just more development there, and we're ready to take on the challenge. And again, I thank the Mexican mines for being tolerant. It's great to work with Fresnillo. It was great to work and do some of our development at on Emisor Oriento, and so being associated with Amitos and being associated with Mexico has helped further on this development in the tunnel boring industry and in mechanical excavation. And Mexico needs to be, the Mexican sort of tunneling and mining industry needs to be thanked for that. You've contributed. Thank you very much.
Thank you very much, Lok. Muchas gracias, Lok HOME, por su presentación.
Thank you very much, Lok HOME, for your interesting presentation. We believe we have some time now. We are ahead of schedule, so it seems we still have some time for some questions for our speaker. Anybody has a question for Mr. HOME?
Parece que no hay preguntas.
Well, it seems there are no questions. If you have any questions, please, you can send them through the Mexican Association Amitos. I think somebody, Dr. Ovinet, your hand is up. Please go ahead.
Si le pueden dar la palabra, por favor, al
Can we please unmute Dr. Ovinet? Yes, go ahead, please, Dr. Ovinet. We hear you now.
Adelante, doctor.
Go ahead, please. Can you hear us? Dr. Ovinet, please go ahead. I have a question, something very simple. The circular system has the advantage of spreading the stress on the rock or on the soil, which is favorable for stability, with a horizontal ceiling is not critical, I believe, regarding stability in the tunnel. Isn't that critical? A flat ceiling, isn't that critical for the stability of the tunnel?
I can tell it in English. When we use a circular section, we take advantage of a favorable distribution of stresses around the tunnel. When you have a flat or square section with the flat top, then don't you have some problem of stability of the rock? Isn't it a problem for the stability of the tunnel, the shape?
Yeah, thanks for the English question, putting it in English for me, but you're exactly right. If you got squeezing ground, if you anticipate squeezing ground and stresses within the rock, then you're certainly better off with round. In this case, they have a lot of experience. It's a mine, it's an existing mine. They kind of know what goes on in their mine in most cases until they get out into new sections of the mine. and they know that they don't have those stresses, or those stresses are rare. So they understood that they understood that if it was a rectangular tunnel, then you wouldn't have problems. But then on the other hand, if you're going to blast a rectangular tunnel, you got the same problem, don't you? I mean, you'd rather have a arched back, and the best solution from stability is clearly round. That's understood. But need for a flat floor is also very prevalent in the mining industry. In the mining industry, and that's why we're looking at the question mark machine that I showed, so that you end up with let's say, the best of both worlds: a round crown roof, Roman arch roof, and live with the stresses on the side as you do in drill and blast. So yeah, your question is right on, and the answer is yes to your question. You certainly are inviting more problems.
Thank you very much.
Thank you, Lok. We have another question from Mr. Marco Tapia from Costa Rica. Please go ahead, Marco.
Thank you. Good morning, everybody. Thank you, Mr. Home, for your interesting presentation. My question goes into the subject of standardization. Do you think this kind of machines, I mean, this with rectangular section, it could be an improvement also for standardization of the industry? I mean, is it possible to think on a stronger market for these kind of machines, thinking in projects in our region?
The answer to that is yes. Why we ended up with 5 meters by 4.5 meters is because that was sort of a standard haul truck for the mines, and you could pass the haul trucks and their drill jumbos and everything. So that's where we ended up with that dimension. And I think you're right. We're going to go ahead in the industry. You'll see more of these, and we should standardize. If you standardize, you get a lot of advantages. First of all, you get the buying advantage. You could probably, if you made 100 MDMs, you could make them for half the price we do now, just because of volume buying and less engineering. Your engineering spread over 100 machines instead of one. So industry has to go standard. And so your question is appropriate. We have to standardize. And I think we'll end up standardizing, just like there's standard drill jumbos, trucks and everything. And I think there'll be standard MDMs or whatever we're going to call them. So I think the industry will trend standard, yes.
All right. I think we have one more question from Joel de la Rosa. He's stating, thanks for sharing your knowledge. Please tell us if the components of the square face boring machine is prepared to deal with the usual mining conditions of hot water and steam.
Hot water and steam is okay in a sauna, but it's the same problem if you're drilling and blasting with an MDM, but it's more controllable. We have hot water and steam in this mine, and but we're heavily ventilated, so we can pull out a lot. We can pull out a lot of, let's say, and cool down the working area. And we also bring sort of our knowledge from deep tunnels in parts of the world of where we've been in this condition before. So we faced hot water and hot steam in several projects around the world, and we know we got to have sort of refrigerated or ventilated or air-conditioned cabinets just to get the workers into that for a period of time to cool them down. And if they're going to be drilling, we know to bring forward cold air, chilled air. So we bring our experience from tunnel boring in similar conditions into the MDM, and hey, it's a problem, and it's a problem if you're drilling blasting, and it's a problem with this TBM. But I think we can control and have a better environment with mechanical excavation than you can with drill and blast.
Okay, thank you, Lok. I think we have time for one last question from Eduardo Salgado. Please, Eduardo, go ahead.
Hello, everybody. This is the question. What are the main parameters of excavation and how the process controlling is managed in the case of Fresnillo?
Not quite clear on the question. Are you asking about the structural relationship between Fresnillo mine, the contractor operating the machine, and us as the TBM supplier? Is that the question?
Si no, también lo puedes decir en español.
The question is, what are the main parameters of excavation of the and how the process controlling is managed in the case of Fresnillo?
Oh, okay, got it. Yeah, so actually the contractor is a new contractor. He hasn't so much experience, but what he did was take a lot of experienced TBM operators from the various projects in Mexico over the years, mainly civil projects, put them together as a team, and they get just paid as sort of a agreed hourly rate. So they have different skill levels on the team, and each skill level has an agreed hourly rate, and they get paid. The contractor doesn't have a risk of low performance. They're on a, let's say, a cost plus arrangement. And as I explained, the mine sort of gave us most of the money for the machine, and we had to reach certain target rates and advance rates to get our full payment. And so it's kind of a risk sharing, cost sharing incentive system. And the mine also gets the contractor can get some bonus, I believe, if he achieves certain advance rates as well. So there's an incentive for the operating crew to, let's say, get as many meters as they can in a day. And there's an incentive for us to make the machine go faster, and the mine is taking the risk. So it's a pretty reasonable arrangement. In all these things, you want to be able to speak to your partners without lawyers and claims and everything. And I can say there's no claim presented to us, and there's no claim presented to the contractors. Something highly unusual for me. I'm used to the civil industry where everybody's claiming everybody. They claim, the civil contractors claim the owner, and then they turn around and claim the TBM supplier. And but they're my friends because they're my customers. So I guess I like claimers. So I hope that answers your question.
Thank you very much, Lok. I think we're finishing. I have just one question. What is the maximum rock resistance that the MDM is able to bore in?
Well, like all disc cutter machines, there really isn't a maximum. I think we can cut 200, 250 MPa rock. The problem is when you get into harder and harder rock, your advance rate just decreases. And so, yeah, it's amplified because in a round TBM, you can sort of tolerate more decrease because in a oscillating cutter head machine, you don't have effectively the same RPM, means that you don't stroke as fast or stroke as fast as you rotate. So the slowdown when you get to harder rock is more amplified.
All right. Thank you very much.
Thank you. It's my pleasure to present. Thank you very much.
Thank you very much. And we'll then move over to the next presenter. Thank you. And the next presenter is Mr. Al Adsam. from the Shimizu Corporation in Japan. Due to the time zone over there, he was able to record the presentation. And if there are other questions, we can send them to him and he will be happy to answer them. Going into his biography, Mr. Edsam has joined the Shimizu Corporation since 2009. With a background as geologist, geotechnical engineer, he has been involved in tunnel projects in Malaysia, Singapore, and currently in Tokyo headquarters, giving technical support to various tunnel sites in Japan and overseas. And we found this presentation also very interesting because there's two machines that are joined together by the tail shield, and then the tunnel go in a spiral to be able to go into some foundation in between some civil foundations. So let's see his presentation. Please, Marco, can you please present it?